Hello, everyone. My name is Minji Chen. I'm a assistant professor of electrical and computer engineering at Princeton University. Welcome to this webinar series 4. It has been a wonderful month together with all of you guys. We went through the kickoff meeting of the MagNet challenge about the equation-based model presented by Dr. Thomas Guillot, and about machine learning model presented by Haoran Li last week. And this week we'll be focusing on data quality and error analysis because we think it's very important for all the teams to understand where the data come from, how do we evaluate the accuracy, because there's always a mismatch between the data and the real world. So for this competition, we will consider this as a game. So although we try our best to improve the data quality, but we can't say our data is 100% perfect. And we actually hope to create this opportunity for everyone. If you have the resources and time and efforts, you can equipment, and you can join us to contribute data, because if you only have one data, you don't know where the ground truth. But if you have 10 data, if you have 100 data, if 100 people trying their best to measure it in the most accurate way with different methods, then we can start to do cross-validation, and we start to know where the real ground truth are. So that's the purpose of today's webinar. So we hope that we can make it completely transparent about our data, and also let you know how do we evaluate our error, and potentially in the future, if you do a similar research or hosting a similar competition, we can also have a deep investigation into data quality. So before we start the presentation, I want to remind you that we do have a 2-page concept proposal due on June 15th. So you should have started drafting it. Again, we're not looking for groundbreaking innovations in this 2-page proposal. We're just trying to make sure everyone is on the same page. And if we see any questions, we'll read those proposals carefully and provide our feedbacks. And if we see any problem, any misunderstanding, we will let you know, so that we will make sure everyone is on the same page. So before we start the presentation, any high-level general questions about the competition that anyone has, feel free to unmute yourself and we can chat.
Hello.
Hello.
Yeah, I have a question about the evaluation criteria and the awards. So the awards include the performance track and the novelty track.
Right.
However, the evaluation criteria include the accuracy, sets, explainability, and novelty. So how do the evaluation criteria associate it with the performance track and the novelty track?
So I will have to defer this to the judge committee. So in the end, we don't want to make it like a algorithm-based competition. We don't want to say you are 0.1% accurate than the other team, then you are the absolute performance winner. We don't want to make it that way. So in the end, the performance track and novelty track will be judged both by the judging committee. So they will jointly consider performance and novelty and generality and model size, and give out performance award and novelty award.
Okay, thank you.
Yeah, so in the end, it's all, we have the option of making it just completely based on numbers, but we don't want to go towards that direction, because that, by creating that criteria, we're introducing bias. So we hope that it can be more of a comprehensive process, where the judging committee, they will discuss amongst themselves and make decisions. If you have any recommendation, we are open to that. Right now, at this stage, we are not 100% confirmed on all the criteria. We're still designing our testing criteria. So feel free to provide us with your feedback. As we said, we want to run this as a community effort. So if you have an idea which can potentially create an unbiased way of judging the teams, we are open to all the recommendations.
Yeah, actually, I think there's a trade-off between the accuracy and the model size.
Right.
But both of them are evaluation criteria. So I think maybe we can write analysis about the trade-off between those two criteria. Will that be helpful?
Yeah, that's a novelty, right? If your contribution out of this competition is about how do you make trade-offs between accuracy and model size, that will count towards the novelty aspect.
Okay.
Yeah. So basically the way we design it is that you can anything, or even if you have a way to pre-process the data systematically with good justification on the algorithms you design, that's also novelty. So I would say the performance track is more about model performance, and the novelty is very general and broad. So anything, new ideas, new understanding about this general problem, we'll consider it as novel, and the judging committee will factor that in. Now, this is a great idea of pre-processing the data. Any other question? Oh, may I ask which university do you come from? I think it's good, like right now, if you have any question or we have any discussion, please self-introduce yourself so we will know where you're from.
Oh, yeah, I'm from Jinan University.
Okay, welcome.
Thank you.
Any other question? No. Okay. Then I will start the presentation. Let me see how I do that. So, can everybody see my screen? Yeah. Okay, great. That's nice. So yeah, today we'll be talking about data quality and error analysis. I'll give a brief overview about why we're doing it and why do we care about data quality and error analysis so much. And then Shukai, who is a grad student at Princeton University, and he has worked with Haoran and Diego in collecting the data. And we will talk about specific considerations and details behind the data quality and error analysis. So we will talk about MagNet database today. We'll talk about VI methods, which is the method we adopted to measure magnetic core loss. And as I said, we open, if your university has capability of measuring data in the same way or different way, we welcome it, and it would be great if we can start to do any cross-validation about the data, because honestly, if you only have one data point, you don't know where's the ground truth. So the error, source of error, we talk about where does the error come from and how much error we are anticipating. And we also report our self-evaluated reproducibility, meaning that we have the same person do the measurement at a different time, or different person do the same measurement with a slightly different way of doing things. So we'll sort of briefly talk about that, and then we'll show how does the core performance vary with all kinds of impacting factor, and we actually have a preprint paper talking about it, and that's sort of why we're doing all of this, why magnetic core loss modeling is so complicated and so hard, and we need everyone's help to really advance our understanding. So about magnetic design, there are three important aspects. One is data, the other is model, and the third is design. And every process we introduce error. So data has error, and coming from the equipment, coming from the way you process the data, any downsampling will introduce error. Any filtering will introduce error. So it's good to have a good understanding of where does error come from and how much, how do you introduce them, and how much error we are anticipating will translate into the final design. There are also model error. If you assume your data is 100% accurate, then any modeling process is trying to use or compress information, right? You're using a simple equation or simple neural network to represent a huge database. You are basically compressing information, and any information compressing process may introduce error. And for MagNet competition, we're actually focusing on model error, because we don't, this year, at least for this year, we don't have the data error evaluation part. You don't have the equipment, or we don't anticipate that all teams has capability of doing the cross-validation of the data. So this competition this year, we are only focusing or competing on model error, meaning that we assume our data is perfectly accurate, or it is what it is. It is coming from a manufacturer or coming from a vendor. Someone give you the data and assume you cannot validate the mismatch between data and ground truth. And all we are evaluating is like, how can we best represent the data we have in hand, and how do we best compress the information from a huge database to a small model, but without losing too much information. Or we can prioritize information. We know some of the information is more important, other information is less important, so that we've put our resources into understanding the important factors. And finally, design approximation, maybe in the future years, like once you have a good model, how do you translate the model into design? And during that process, we're usually making approximations, and how do we make those approximations? Could be one of the competition tasks in the future. So again, for data, there are three types of data. There are data sheets, which may come from the manufacturer. Some manufacturers may have software, and there are data coming from publications. And usually the question we receive is that how does all of your data compare to data sheet data? How does your data compare to software data? And how does your data compare to other people's publication? This is a very good question, but we usually do not have a really good answer, because for people who are less familiar with the magnetic material industry, you know that the data sheet, when the manufacturer reporting their data, they are not really applying statistics or like data-driven methods or mathematical tools to really report the data. They are sometimes reporting the data as the worst case. Or in other words, the data you see on the data sheet, not for all the manufacturers, but for some of the manufacturers, based on the conversations we have with them, is that it's the worst case scenario. If you buy a material, you usually overperform what they reported in the data sheet, meaning that data sheet is not accurate. It's actually reporting the data in as the worst case. So if you are targeting a precise design with limited space, maybe trusting the data sheet is not the best option, because it's not what you're going to get statistically from the market. So for the software, again, it's a similar issue. Like if we ask the manufacturer, where does the data come from? They may say, oh, some of the data comes from real measurement. Some of the data come from calculation. And we ask, like, how do you calculate that? They say IGSE. So again, if you find data from software, it's very important to ask where the data come from. It's very likely that some of the data come from calculation, some of the data come from measurement. And the manufacturer is reporting in a way that anyone has a bias, and manufacturer absolutely has a bias. So it's not I would say we are facing a problem where really it's just complicated science and commercial purposes and standards of practice. A lot of these comes in and making us, it's very hard to justify or really make sure how to report data in the best way. I would say they are IEEE Pell Standards Committee working on how to improve the way we report and document data, and hopefully this competition will shed some light in those directions. And finally, for publications, again, different researchers report data in different ways, and they treat data in different ways. Some of them will do sort of data cleaning first, like get rid of the outliers first, and I guess many of us do. But on the other hand, if you're getting rid of outliers, the question will be, how do you get rid of the outliers? What are the criteria? And different people use different criteria, and as a result, the data quality in the end across different applications are very different. So what we hope to emphasize is that it's very important to consider. So now we are facing a big data problem. In the past, when we were thinking about IGSE or statement equation, we're talking about mathematical problem. But if we want to push this to the next level, we really have to think about this as a big data problem, and we need a systematic way of thinking about data quality. So that's the motivation, pretty long. And we have the measurement methods, and the method we use in our lab, which is used to support this competition. We use VI method because we are particularly interested in non-sinusoidal waveforms, and we hope to fully automate the data acquisition process, and turns out the VI methods with the oscilloscope or the time domain method turns out to be the most attractive. So we do have limitations. Like that's why we limit our flux density range, we limit our frequency range. We only have sinusoidal, trapezoidal, triangle, trapezoidal waveforms with different combination of duty ratios and temperature and flux density and frequency. And we do have DC bias capability, but we're not 100% confident right now. So this year we don't include DC bias in the competition, but in the future, we may add DC bias. So right now, our data acquisition system can capture one data every 1.2 seconds. Well, for the experts, you probably know that magnetics has relaxation time. So we can push it faster, but that's where you hit the point where we think the relaxation process or relaxation of the material will start to have a significant impact on the core loss. So that's why we sort of limit it to 1.2 seconds. So any teams who are interested in dive deeper in this field, you are welcome to propose your own methods. And you can even mention that in your report. If you end up really spending time cross-validating the data, we welcome that. And that, again, will count towards the novelty side of it. Like, how do you evaluate the error? How do you really evaluate the data quality in the right way? We consider that as a novelty, which will contribute significantly to this field as well. So yeah, that's the data acquisition. So VI method, for many of you, you probably know, we measure the voltage and convert the voltage into B. We measure the current and convert the current into H. And then we take the single cycle of each of them. And you may know that, well, once you convert a long cycle of measurement into a single cycle, you are introducing error. And Shukai is going to talk about that. Like, how do you sample it? How many samples you sample per cycle will have an impact at some point, right? So everything we do in this process introduce error, and it's important to understand where the error comes from. And the algorithm you use to take that one single cycle from a long measurement will again introduce error. So for this computation, we're not getting to that because we are providing a single cycle B and H information, and we hope all the team just assume we're doing it in the right way. But I want to mention that we don't think we're doing it in the best way. There are huge room one can improve, and there are a lot of signal processing tools which comes in, but you have to understand physics, because dealing with audio information is very different dealing with magnetic measurements. So I would say that even before the data, for the data processing, how do you convert the long sequences into a single cycle? Or maybe you don't want to do it at all. Maybe you just keep the long sequences as a raw data and get the core loss from there. It's better than doing the single cycle for B and H and integrating them. So we're open to all of these discussions. But as I said, like, for this competition, we assume all the team will take the data as granted. We'll not trace back to how do we get this data, because we know there are errors introduced in this process. Right, so this is how the database right now you have. So for the MagNet challenge, we have put the data in the Dropbox link. So if you go to the GitHub link, you can find the Dropbox, and you click on the Dropbox, you can download 10 zip files. So that's the data we provided for the competition. So we do have a more complete data set, which is now open source at magnet.princeton.edu. It's another repository intended for research purposes. So if you want to get the complete data and all the information about the geometry of the core and everything, you can go there and download data from there. It's the same data on this repository and in our competition, but just like get rid of some information that we think is not important for the competition. But if for research purposes, if you're interested in the raw data, you can go to the other website to download from there. So understanding the error, that's the main focus of today's talk. So all the data points has an error range. The tricky part is that this error margin, because this is a multi-dimensional problem, like you think it's 100 millitesla, but you may not measure it exactly 100 millitesla. You think it's 25 degrees C, but maybe it's 26 degrees C. So there's always error margin on every dimension. of the measurement, and that's why doing rigorous systematic error analysis is still still an open question, and we are just providing example and providing or sharing the information that we know to all of you guys. So yeah, with this, I want to pass this to Shukai, who's going to talk about the sources of the error and how much error we expect from one of the material. Like we have 10 materials. We think we have done error analysis for 3 or 4 of the materials. So there are rooms that you can do. If you find interesting phenomena in the data, feel free to let us know. It's very likely that there are problems in the data. But this is, we hope to embrace all of these problems, because this is the same thing will happen in the future. If all the manufacturers start to report the data, you'll face the same issue. You look into the manufacturer data, you find out, oh, okay, there are errors in there, there are interesting phenomena. And I guess the more people spending time on this, the clearer we'll have in terms of developing a good understanding about this problem. So yeah, with this, I want to pass this to Shukai. And Shukai, do you want to share from your screen or?
Yeah, I'll share it from my screen.
Okay, great.
Sounds good.
Yeah, let me know. Are there any questions? No? Okay, yeah, go ahead, Shukai.
Okay. Thank you, Professor Chen, for handing it off to me. Just to add on to this, because our measurement system is not able to actually accurately present a error-free measurement, what we could do is to, as mentioned before, what we could do is to compare our data with the data sheets with other stuff. But because these data sheets, usually their accuracy is not always reported, and we do not really have a good one-to-one comparison. So that's why our data really do not have a true ground truth that we can compare it to. So today I will talk about several sources of errors that could contribute to this loss error that we currently have in our measurements. These errors may include, for example, the probe delay, the errors happening in post-processing as we are putting into one single cycle. We could also generate from the oscilloscope we're using, the parasitics of the measurement system itself, the voltage and current measurement. So the circuit, from the circuit perspective, also the temperature, as well as part-to-part variations as well. So today I would first like to talk about the post-processing.
Wait a minute, there's a question.
Oh yeah,
we'll just answer it. Ayo, go ahead.
Hello, I am sorry. I have a question. I didn't understand, sir, when you said there is no ground truth data.
There's no ground truth. We don't know.
Yeah.
There's the absolute ground truth.
Okay.
Because we only have one person. We measure it with us. Like we measure it. We don't have. There are no other database available with the same level of granularity we have. There are probably 1 or 2 data or 10 data or 100 data, but we're talking about 500,000 data here. And we don't know where is the ground truth.
Okay, I see. Okay, thank you.
We tried our best, but without the second people, you can't just say my data is the best data.
Okay, I see. I understand. Thank you.
Yep. So where are you from?
I am from France, in Lille University. I work in L2EP laboratory.
Okay, sounds good. Thanks.
Thank you.
Thank you. So I will continue. So first, I would like to talk about the post-processing error that could come from this. So first of all, we want to talk about the post-processing from our raw data that we collect, as we need to understand how we actually obtained this BH loop information so that we provide to you guys as a single cycle data for any training purposes. So here is just an example of a trapezoidal excitation. So in order to, for example, in this case, we have a voltage waveform, and then the current waveform is in the trapezoidal for the excitation for the core under test. So in order to really obtain the BH loop data, we first have to collect voltage and current waveforms for each one of our data point. And as the initial waveforms for both voltage and this current waveform are saved with few identical cycles, as you can see in this case. And this is obtained directly from the oscilloscope. So to plot the BH loop, And to train the neural networks, we need to construct a single cycle for the B and H waveforms. And so to obtain it, first, we need to, a single switching cycle for the measured voltage and current has to be first extracted. So then from our raw voltage and current waveforms then have to be split into different switching cycles based on the calculated switching frequency that we have in our post-processing code. Then for each one of these switching cycle, then the waveform is interpolated for each cycle into 1024 samples. And then finally, this 1024 samples for each one of the cycle can then be averaged into a single switching cycle waveform as shown on the bottom here. So the post-processing of the voltage and current waveforms can have impacts on data that are hard to quantify, but definitely should not be overlooked. And this type of error may come from when we are actually calculating the frequency of this particular waveform. So the algorithm essentially, for this case, when we put it in the single cycle waveform, will boost our vertical resolution and also save spaces, as mentioned by a student before, because there's a trade-off between the size of the data as well as the accuracy. So, but if the frequency is not accurately defined for each one of our cycles, then there's a problem, because if we do not identify each frequency and we cannot bifurcate each one of these cycles equally, then the waveform in the first cycle may be a little bit different than the waveform in the second cycle. So when we interpolate and average these cycles together, we may actually distort the true waveform quite significantly, so that the actual single cycle waveform that we obtain at the end no longer looks anything like any of these cycles that we saw from the raw data. So when this happens, what we do in our post-processing is that we first have to compare our single cycle waveform with the cycles that we have from the raw measurement. Now, if this differs significantly to the cycles that we have from the raw data, then we have to discard such data point. So for example, if you see some of these core loss data lacking a data point, for example, in here, specifically lacking a data point, that is usually because during our single cycle data extraction, our waveforms were discarded due to the sampling, due to this post-processing error that we have. So then once we obtain the voltage and current waveform in the single cycle, then we can calculate the instantaneous flux as a that is proportional to the voltage, and then the H is then proportional to the current, directly proportional to the single cycle current that we have. And so in this case, what happens is we are sampling our data at 1024 data points per cycle. Now, this is relatively good, really good resolution as shown on the bottom left here, but usually for a regular waveform as seen here with a regular BH loop without significant changes in its saturation area, you can see that if we were to actually downsample this further into perhaps even more extreme case shown on the bottom right here, if we downsample it to maybe 64 samples per cycle, we may see quite a distorted BH loop here. But in fact, because the core loss is calculated as the area of the BH loop, now if you actually look at the core loss compared between the two, you realize that the core loss actually do not change so significantly. But this is not to encourage you guys to actually downsample from the 1024 even further, because there are some extreme cases where the BH loop can actually look quite different than what a normal BH loop may look like in this case, so that if you were to actually downsample it further, it would actually lose a lot of information, and which I will talk about as an example in the next few slides.
Shukai, I have one thing to add. So we talk about trade-off between performance and model size. One way to greatly reduce your model size is to downsample. But as Shukai said, downsample introduce risk, and how much risk you are introducing depending on the material. Some materials may be very sensitive to the high frequency waveforms, and other materials may be less sensitive. So maybe you want to do first look into the signal and do a high level evaluation of the material first by looking at the data and evaluating it. And then for each of the material, you will decide how much you want to downsample it. And this may be a systematic method that we're looking for. So if there's a new material, first you will do a high level evaluation, and then based on your evaluation, you decide how does the model look like, either for your equation model or for your neural network model, to reach a good balance between model size and accuracy. So this is highly depending on material. So we can't say all the 10 materials we provide will have similar performance when you are downsampling the data.
Right. Yes. So yeah, so that's a really good point. And so besides, now these are actually the sampling could cause an error, and from post-processing could cause an error. So besides these post-processing errors that we have, we also actually have more errors that we can see from the measurements themselves. So one of the problems that our voltage current measurement actually poses is something called the phase delay error. So the phase delay error happens when you have an oscilloscope and you're collecting the voltage waveforms from one probe and the current waveform for another probe. And there's always some delay, small delay between this voltage and current measurements because of different probe length or just the scope sampling itself, and perhaps other type of probe related issues we have. And now this delay can actually give rise to a large average power difference. So as you see on the top left here, if you have if you do not consider probe delay, then your voltage waveform may be shown as red, and your current waveform in reality perhaps is the solid curve in blue, IL here. But if, let's say, you do have voltage probe delay, which is always going to be the case, then your true current measurement with respect to the voltage will actually be phase shifted from its original position shown in the solid curve here. So then that little phase shift can actually cause a different averaged power when you're calculating that power loss here. So as shown on the bottom left here, instead of having a true core loss, P loss, you may actually have some more or less even positive or negative losses comparing to the actual loss that we have. So that in this case, if you may have more power loss, that is actually not the case if you are to actually measure it correctly. So this probe delay can actually be quite a significant problem, as the changing in losses is directly proportional to the voltage, the current, as well as the time and delay and the frequency. So as you increase all these parameters, your changing in losses is going to be dramatically increased. So as a result, the delay poses a significant problem when it comes to if you were to operate in very high frequency, or if your losses for the material is very low. So for example, that was for the sinusoidal case. The same similar effect is happened for the PWM waveforms as well. So as for example, here we're showing a relative error in our measurements due to our phase delay. So as seen in this case, this is the distribution of the relative errors for all the data points that we have collected. So as seen here, in the specific subset of database, we can observe that the maximum error that we see due to the probe delay is about below 5% for an estimated delay of 1.6 nanoseconds that we measured between our two probes here. So
this is assuming we have 1.6 nanoseconds. So we're taking the data and we're assuming that we can, for any random reason, we can have up to 1.6 nanoseconds of delay, how much error we are expecting to see across the entire, this particular example map.
Exactly, exactly. So this is just a specific example under the specific operating conditions, the same duty ratio and the temperature and etc. Now, we cannot really say this is the maximum error that we have for our system, because this is just a distribution for our data of the error for our data at a specific under specific operation condition. If we continue to change the operating conditions, we may then have different relative error graphs as a result. So just a number is not really enough when it comes to reporting the error for our wide range of conditions and materials when we have 500,000 data points. And only providing the maximum error may not be quite representative of the whole database, as in we may not have as significant of an error distribution in that region as to the rest of the database. So plus, it's not really always easy to find that operating condition that give rise to this worst case conditions. So this 4% is just a is not really a metrics that we look at. We really look at where does our relative error actually be the maximum. So in this case, we can see that as you increase the frequency, and if the material has low loss, then you will definitely see a more significant error in that region than the rest. So for this, we have to really be careful with how we actually evaluate the phase delay.
But for this competition, we don't have that here. Yes. For the competition, we're assuming that we are perfect. We don't have any phase delay. And you don't need to, this won't have an impact on the algorithms that would develop in this competition.
Yes. Overall, the data that you guys receive is what it is, and you just base yourself completely on that. This is just the potential errors that our database may pose, and it does not have to do with the challenge themselves when you're using the data. So this, if you were to actually impose some type of delay, for example, in this case, we artificially added a large delay actually to the system. You can see that adding this delay, our BH loop can actually be distorted significantly. Not only does the area over the BH loop changes, but the BH loop may have some unreasonable crossing points due to the delay. For example, in this case. So that is really some problems that this phase delay can pose when we're actually doing our post-processing for our data. But it is okay for our database, as you guys can just base that off on this database for now. But do be careful if you see any crossing, do be careful. That may be caused by some errors that was due to the probe delay here.
So for the competition, what we find is that for the majority of the case, because this year we only focus on core loss. So although the BH loop may look interesting and strange, but if you calculate BH area, it's actually maybe 1%, 2% error in terms of core loss. So you can still use those data, and those data may still be legitimate in terms of core loss prediction. But in the future year, we do think maybe we'll do a BH loop prediction, then this becomes really interesting.
Mm-hmm. Right. Yes. So besides the probe delays themselves, we also have issues that comes from the oscilloscope. There are numerous errors that could come from the oscilloscope. In this case, we're using the Tektronix oscilloscope, and the data, the way we collect the data is because the oscilloscope will collect the voltage and current waveform. So how this data is captured will also impact the quality itself beyond the probes. So the oscilloscope used and the scale selected really determines the vertical and horizontal resolutions. But there's also other errors associated with this as well. So as before, we can see that obviously a single number for the expected error cannot be provided here. But if we find this error, we can also look at the manufacturer's data sheet. So finding this error is actually quite challenging in the sense that the oscilloscope manufacturer actually only provides a maximum error as shown in the error analysis here. So regarding the overall error here, both the probes will obviously introduce some error in the measurement, but the oscilloscope also actually contribute significantly to the error. As you can see, besides the 1.5% of error just from the reading, and a fixed about 1.2 millivolts of error introduced to your overall system, there is a really crucial 15% maximum of error that can be introduced from the vertical scale. So first, we have to know how does this vertical scale selected. So the vertical scales are selected based on the amplitudes of the signals that we measure. So and it depends on the operating point as shown in the two figures in the left. So the figure on the very left shows how do we select the voltage scaling for the voltage waveform measurement. And then the middle one is the scaling for the division for the current measurement that we have. So each one of these will actually both contribute to maximum 15% of their own division scaling error when it comes to the core loss, when it comes to the data measurement. So as you can see, the changing in colors here represents the switching from one voltage scale per division to another voltage scale per division. So from the data sheet, this error has really big part that associated with the divisions here. So if we were to go from 2 volts per division to about 20 volts per division, we have to be mindful that every time we go up in terms of the voltage, the scale, we have to impose that 15% of the error from our oscilloscope. That's the maximum error that we have. But if you were to calculate the loss, that is using both the voltage and the current measurement we have, then suddenly your loss your loss error will actually be contributed from both the voltage and the current measurement here. So if you were to actually check how smooth the data is, you can see that the most abrupt changes in this data accuracy on the right side here, the most abrupt changes usually happens near where the scale of the scope changes, so that when that division error actually plays a bigger role. So to wrap up here, we can see that we really should pay attention to this type of error when it comes to scope selection, as in this 15%, it's actually quite significant. However, we can't really say every single one our data point has contributed 15%. As clearly see here, we do maximum is about 16%, but there are many that are below that, because this only represents the maximum. And for every single one of the data points that we select, we don't know what is the true distribution of the error for each one of our data points under different operating conditions. So this maximum error could only really give us a ballpark of what's the worst case that we have, but it's not representative of the rest of the system because their distribution is really unknown to us. So this really depends more a discussion and research in the future as well.
For the competition, again, this doesn't really matter. This is the mismatch between the data and the real world. And the real world, again, has batch to batch variation and material to material and sample to sample variation. So for the competition, we assume that our data is the ground truth, and hopefully your method, which is developed based on the data we provided. In the future, if someone else is capable of providing a data which is 1% error, is very, very accurate, hopefully your method is still solid and applicable. So we try to decouple. One of the vision that we have is we try to decouple the challenges of getting accurate data and the challenge of developing good models. So for the competition, you just assume that, well, yeah, this data is whatever the data you have, and it's the best data you can get so far. And hopefully next year or in the future, if more teams joining us, we can have more cross validation. We know where the true ground truths are.
Mm-hmm. Yes. Yeah. So that is the error associated with the oscilloscope themselves. And beyond the oscilloscope and other measurement tools, we also have to consider the effect of the parasitic elements that are in our circuits, because parasitics can also add significant measurement errors. And it's interesting to see how this is the case. So first, we can do a observation on the voltage measurements here. So ideally, when we have a two-winding method, we're assuming that the secondary, when we're measuring the voltage, the current through the secondary loop is 0. But in reality, when you are measuring the voltage across the secondary, you will always have some probe capacitance or resistance associated with that secondary, as shown on the right side, top right here. So that means, as a result, the current through the secondary is no longer absolutely 0. So this implies that the current measurement on the primary is not only related to the H field, but there's also a little bit of current that's exciting the core from the secondary here. So that this may actually introduce a little bit of measurement discrepancy when it comes to comparing the current waveform we have and the true current that has excited the core itself. Now, the second thing is on the current side. So what we have is a current shunt measurement, and this is essentially guarantees that we have very high accuracy for our current measurement. But nonetheless, parasitic capacitance and inductance will be present in this shunt resistor here, and especially for the parasitic inductance that's in series with it. This may introduce the inductance may introduce a voltage drop across, so that when you actually measure the current through the current shunt, what you measure may no longer be the true current that is actually been exciting the core from the previous stage. So that in this case, you could introduce error to your current measurement. But the coaxial shunt that we selected is for 800 megahertz, and our operating frequency only goes up to 500 kilohertz, so it is not so worrisome for our case here. And the parasitic capacitance in the core, as well as across it, also impacts our measurements. So if we have a parallel capacitance that is shown here, then our measurements on the current there may be some current that's flowing through the capacitance and not the core itself. So when we measure the current, we're still measuring the overall current throughout the system, so that the true excitation may again not match with our core itself. But usually it is important to sort of minimize this capacitance so we do not have such an issue. And the capacitance actually plays a bigger role in terms of the dV/dt effect than what we have here. So all these parasitic components should be considered when we were designing our system, so that we can ensure the errors from the parasitics can be minimized here.
So for the competition, all the data we measure is the true measurement. So it captures this parasitic impact. And in your real design, you always have capacitance, and this capacitance does contribute to your converter losses. So it really depends on what you want to do. If you want to design a model which help with your design or estimation of the loss of the converter, this is what you need. But if you want a model which is really understanding the physics, then you probably want to separate the impact of parasitics and the impact of the hysteresis. So for the competition, we will not get into this because we are really caring about material behavior. So what we provide is the BNH after post-processing. You know, when you are converting voltage into B and current into H, we are introducing error there too, because voltage and current is a component level parameters and a state variable, and B and H is the material level state variable. So when we're converting V to B, we are assuming uniform flux distribution within the core, which is sometimes not the case. We are ignoring or lumping all the parasitic impact. But I would say there are a lot of open questions there every step when we deal with the data, when we start to caring about how much error we're introducing.
Yep. So the error is truly in every part of our data collection system. And in fact, this capacitance effect actually plays a big role when we consider the actual current waveforms. When we actually collected the current waveforms and plot our BH loop, this capacitor effect actually does play a significant role. As you can see here, this capacitance, as you do your switching, during your switching, this capacitance actually can introduce huge dips in our current, as shown on the top right here. So here's an example of a triangular waveform that we have. So blue is a waveform transition that is not so sharp, and as you go towards more red, that is when your switching transitions, your voltage waveforms becomes sharper and sharper. As your voltage waveform becomes sharper and sharper, you introduce more dVdt due to that capacitance that you had.
Not just that capacitance, but also the material behavior. So the capacitance effect can come from parasitic capacitance of the DUT. The material itself may have some capacitance effect as well. And we don't think there's a theory which can allow us to completely separate the two. So the two capacitive effect, the material itself may have some internal capacitive effect as well. So we don't separate them here.
Right.
From design perspective, it doesn't matter because you may have a converter which switch at high dVdt and you capture both. You want to consider both the parasitic capacitance effect and the material parasitic effect. But for physics, then maybe you do want to separate the two so that you can understand either of them.
Mm-hmm. Right. But this capacity effect really creates a huge problem when you have a sharper transition, so that they create a huge dip in the current waveform. So that is reflected on your BH loop actually. If you have a deeper dip in your current waveform, that is, if you look at the BH loop shown on the bottom right here, not only does the shape of the BH loop change, there also introduces some sharp spikes here in our BH loop, so that affects the area over the BH loop as well. So in this case, we've seen almost about 10% more losses from the red BH loop compared to the blue one. And this is especially important for you guys who, because if you were to downsample your data even further, this information, if you see a big spike here, then this information may actually be lost. And so your actual modeling of the loss may not be as accurate as you were to have a higher resolution for the system. So this actually, if you have big spikes, for example, as the red one in our database, we do have some of them. If you were to downsample them further, then we may see you may have lose of information, and then at the end, your data, your model may not be as accurate as you were to have a higher resolution for the data itself.
Yeah, so maybe we're not recommending or anything, but maybe you can do FFT first and look into how much dVdt and how much harmonics you have in a waveform, and then based on how much harmonics, you choose the particular algorithm that you think fits the best. Mm-hmm. So in the end, keep in mind, we are evaluating the model size based on how many parameters you have. You can have sophisticated algorithm. You have 100 parameters, you have 10 parameters, but the algorithm can be very complicated. And that's the innovation we're looking for. So your algorithm can be complicated, but we hope that you don't store too many parameters about the material.
Right. So on top of this, so this becomes a problem, right? Because now when you have such dips, then it implies that our definition of waveforms is quite important. Because now with this dVdt, our triangular waveform is no longer going to be ideal triangular waveform anymore. So with this type of problem that we have with the how do we identify our waveform, there are other sources of non-idealities that can also introduce to make this definition of waveform more complex. So one of the problem could be the shunt itself, which creates a voltage drop that is proportional to the current. We also may have a power amplifier that distorts our sinusoidal waveforms so that your sinusoid is no longer going to look like a true perfect sinusoid. We also have fixed clock times with limited PWM resolutions. There's also dead times, which affects the different transitions. So all these actually can play a big role when it comes to how do we, when it comes to trying to define a perfect triangular waveform or trapezoidal waveform. But these are already in our database, so, and it is what it is, and you guys only need to base off of what we provide. And this is just for research future discussions.
Yeah, as we said, this is one of the reasons we don't provide tagged data. So many teams asked us, like, can you help us to tag the data? We said we don't know how to tag it because with different DVDT, the trapezoidal A is very different from trapezoidal B. So you may not consider all of them as trapezoidal because they are not trapezoidal. So we don't know how to. We're open-minded. We hope some of the team can teach us how do we tag the data in the best way.
Yeah. So that is very important for our waveform, the definitions here. And so besides this type of definition of the waveforms and other measurement issues, we also have the variation of temperature. As we know that when we measure our temperature for our data collection system, we place our core under test in a oil tank. And we put this in an oil tank so that the heat can be distributed into the oil nicely. But if you were to actually introduce a lot of loss, you can see that the core actually heats up quite a bit, shown on the left here. Now, the oil solution is a good solution, but because what we're doing with our excitation is that even though we're exciting the core with relatively short period of time, 1.2 seconds per data point, but because we are actually collecting these data, we're constantly exciting the core one after the other with different measurements, our average core losses during the testing will heat up the core itself over the oil temperature that we set it to be. So that one of the solutions that we had was actually to add a magnetic stirrer. And with that, as seen on the right side here, we're actually able to keep the oil temperature relatively low and make sure the oil distribute that heat out into the rest of the tank so that we don't have a hot spot in one specific spot. So this is especially important because temperature can actually vary your core losses significantly. Just 1 or 2 degrees can cause errors. And this is, but the problem is for our system right now, we're able to keep this temperature as close to what we wanted as we can. But in reality, the temperature is perhaps not too well controlled in our database because we don't really have a good estimation of the delta T here. So 25 degrees may, in our data set, maybe perhaps 25.5, 25.6. So this type of temperature variation can also give us errors. So we have to acknowledge this in our data publication, as in the temperature that we have perhaps is not needs to be addressed with a better estimation of the delta T as well.
So temperature, we have four levels, right? 25, 50, 70, and 90. So what we do is we use the external temperature control facility to keep the ambient temperature at 25, 50, and 70, and 90, and we excite the core for a very short amount of time, so that we hope the core temperature is not changed because we are heating up the core. But on the other hand, we think it's 25, but it may be 25.1. And there are also questions about, like, how about the temperature gradient within the core? And that's very important. Again, if you're caring about the design, then what you care is the ambient temperature. In any practical design, you always have temperature gradient within the core. So you can lump all of these in as effective temperature impact on the core loss. But if you try to understand physics, then you probably do care about the gradient distribution. So what we report is the best we have, and we are open to any innovative ideas or anyone who has the capability of really give us a better way of measuring the temperature dependence of the core loss.
Yes, indeed. So after all these introducing all these sources of errors, we have to really assess the reproducibility of our data acquisition system here. So as you see on the bottom left here, here's an example of us using the same exact core and then have the same number of turns for our windings and measured across a frequency and flux density range at the same temperature, same duty ratio for the same waveform, and we repeated that 5 times. So as you can see, with this distribution, we can see a overall less than 3% of error in this subset for an instance. So that tells us that our data acquisition system at least can make our is not varying too much in terms of measuring the same core, so that our data acquisition system is actually highly repeatable. Our data is highly repeatable here. And this is the message that we're trying to get across. But if you were to actually want to observe all the errors that we may arise from parasitics or temperature and the others, what we could do is to change the number of turns from between 3 turns and 7 turns. Because when you have different number of turns under the same condition for these identical cores, for this identical core, what happens is your voltage and current excitation will be different from the one with 3 turns and the one with 7 turns. So sometimes these parasitics can introduced errors can arise from these different voltage current excitations. But as you can see, even though we've said some of them may have a maximum error of 16% or very high percentage of error, but if you were to really test this, you can see that for the same core, the actual error for this specific subset is below about 8%. So this actually tells us the actual error from our data collection system is actually not as high as what you may think the maximum error, the worst case may be, because this is all depending on the distribution of errors in our subsets. And in reality, we're not introducing as much error as we thought we were.
So Shukai, there was a question. Is it safe to assume we will only be predicting the for temperature given, not interpolate or predict arbitrary temperature? And the answer is yes. So for the testing case, it will be the same for temperature that we gave. We know there could be very interesting phenomenon happening on the temperature side. So yes, so for the testing, we'll be focusing on this for temperature.
Mm-hmm. Yes. So yeah.
So the other thing regarding Shukai's comments on the error. So keep in mind, when we evaluating each of these single error source, we have like 10% error here, 10% error here, 8% error here. So all these error is like Gaussian, or we actually don't know the exact distribution. They are random distributions there. So we're reporting the absolute error. So in the end, this is like multiple noises going together. So all the noises, the worst case is not happening at the same time. So they may happen at the same time, but for a majority of the case, what we think for most of the materials, we are thinking our error is probably 10% to 20%. So lumping all of these factors together, up and downs. So some of the errors may even cancel with each other. So that's why we are so confident. We are probably getting to a point where we can start to trust our data. So our sample to sample variation is probably like 10%, 20%, and our error is probably in a similar range. And maybe in the end, for equation-based model or neural network model, machine learning model, like targeting 10% will be a realistic goal. Between 5% to 10% accuracy will be good. Our goal is that our measurement at least should be a little bit better than batch to batch variation, so that we can start to quantify batch to batch variation. If your measurement is like 20% error, and you can say your batch to batch variation is 20% because 20% may come from your measurement. So we at least need some model and measurement capability to beat the sample to sample variation, which we do think we are capable of doing that now.
Mm-hmm. Which is what I will introduce in the next slide, which is our different batch to batch or even core to core variations. So this is actually quite significant when we're considering the accuracy of our database, because when it comes to the database generation, we have this part-to-part variation, as in that when you're testing the core, you would always like to test the same core, so to make sure your accuracy is ensured for this database. But if you were to actually take the manufacturer's equal cores that they provide to us, the whole batch of cores, if you were to measure them against each other. As for example, that we did in our case, we took 5 of the same equal cores claimed by the manufacturer with the same materials and the same geometry that they provided to us. We put each one of them against each other and we tested it under the same condition. You can see that from a core-to-core variation here, we can see almost a 20% of variation just between one core to another core that is even just same core provided by our manufacturer. And this variation might come from the geometrical tolerances or the manufacturing processes that really set the target frequency. For example, in this case, when they give us the geometrical tolerances, we can see that even the volume may have a plus or minus 10.5%. So that now this 20% really is above what our accuracy for our database is. So as Professor said, this really does play a huge role when it comes to evaluating how accurate is our database. Because if we have a large variation even between among the same cores, then we really don't have a good way of saying whether our database is not accurate. So.
But on the other hand, I think this is a good motivation. Only if you can start to measure it accurately, you can start to push the manufacturers or start to classify the materials into grade A, grade B, grade C, grade D. So we do see a strong need in improving the way we deal with data in this field.
Yeah. Yes. So in conclusion, we know that the differences between our measurement data and the manufacturer data is really unavoidable. And there's always a mismatch depending on the materials that we have, the operating conditions, and it also always varies case by case here. So the mismatch could come from, for example, the measurement error that I set up from the probe errors, from the oscilloscope errors, or it comes from the temperature controls that we have, or even the batch-to-batch variation that I just introduced. So so we try to really uniformly control our data quality across all our data, all of materials that we have for the MagNet database, as well as the database we provide you guys for the MagNet challenge. So for now, for you guys who are doing the challenge, please just assume our MagNet data as the ground truth for this, because for this competition, we're really focusing on the modeling. Perhaps in the future, we will be focusing on these other issues that actually may contribute to our MagNet database. So to sum up, we really do have to find a standardized format to report our data and to include our errors. Our goal is not to really achieve 100% error-free, but our goal is that we want to be as accurate as we can, but we also have to be transparent about the process we collect our data, so we can report all the errors to you guys, so that you coming in to collect our data has all these errors in mind, so that we do not mislead you guys when you're doing your future researches. So that is all, and thank you for your interest.
Great. Yeah, thank you, Scott.
Thank you.
Yeah, so I guess this is all we have. I would say, as we said, please take the data we provided as the ground truth. So we will not try to question the data. It is what it is. Like, we're not the great manufacturer. We're just the average manufacturer. We're doing the average job and we're providing the data. Think it in that way. But on the other hand, we are confident that you can learn we can develop new knowledge about magnetic core loss through this process, because the data we reported, we do carefully try our best to improve the quality. We think we're doing better than some of the manufacturer. We're pretty confident on that. And we are getting into the range. Our accuracy is getting into a range of batch or sample-to-sample variation, which we think it's probably good enough for a majority of the designs. But we're open to all the recommendations and feedbacks on this. There are a lot of things we can improve in many aspects. So yeah, that's all we have. Any question? We'll open the floor. So as I said, like, we will not the test, similar for the temperature and for the frequency and flux density. So for the final result evaluation, the data you will receive will be very similar to the data that we gave out. So you don't need to worry about that. We are creating a problem that your model has never seen. No, your model will see a similar problem, similar data before.
So I have a question.
Yep.
So you, considering the loss measurements, are you calculating the losses from now, or are you really measuring it somehow in the oil bath? Because you could do it somehow in a transient calorimetric method, because you basically already have an oil bath.
Yes, we do have an oil bath, but we also don't trust oil. We don't trust the calorimetric method neither. We welcome anyone who want to do it because 0.1% temperature mismatch measurement can create a huge error there too. And how to control, it's like we look forward to see a cross validation from a different method. That's great. But for this competition, to answer your question, the way we calculate the loss is that we got a single cycle B and got a single cycle H, and we integrate the area. So that's the way we get the loss. But calorimetric method, I would say 20% error in calorimetric method. I don't know how to achieve that neither. So at high speed. So again, in order to evaluate the entire data quality set, you need to get 500,000 data from calorimetric method, which is also equally hard.
Okay, thank you.
Yep.
Yes, on maybe just as a small precision for the calorimetric method, I work on that before. One of the main limitations that they have is they give you the losses. They will not give you hysteresis cycle, which for this year of the competition, we only cares about the losses, but the goal of the MagNet challenge, if you look at the research that has been done around, a lot has been also going on for hysteresis cycle. And this is one of the main limitations of calorimetric methods, that they are probably, in my opinion, easier to trust, but they will never give you the electrical parameters of the core.
Right. So in the long run, I think just in terms of research vision, I think doing calorimetric method for building huge database is very challenging, but the calorimetric method is a really good validation approach. So we welcome any team who has the capability and resources and experience in helping us maybe measure 100 or 1,000 calorimetric data points. And now we can then cross-validate the data and get a better understanding about the error. So Jacob, where do you come from?
From Silicon Austria Labs.
Oh, great.
Yes, cool, thank you.
Hi there, sir. I have a question.
Mm-hmm.
This is Jun Wang from University of Bristol. Thank you for the presentation. I just wonder, how did you correct the phase discrepancy between the voltage and current measurement, since it has a significant impact? Could you kindly comment on that?
I think we calibrated carefully. Haran is here. Haran, maybe you can answer this question.
Do you mean the phase delay?
Yes.
Phase delay.
Yeah. So what we actually did, are you asking how do we get that 1.6 nanoseconds of delay between the probes?
No, 1.6 is assumed, right? That's assumed phase delay. That's for analysis. Yeah.
We actually also measured it.
Okay.
So what we did was we have we actually generated a square wave, and then what we do is we use a probe. We use both probes to probe the same voltage waveform, and then when we look at the oscilloscope, we measure what's the delay between one probe to another, and that's the 1.6 nanoseconds we're able to obtain. So
but
we're measuring the same.
That, right? You can just deskew it, right? If you measure it, you can get rid of that.
Yeah, you could. Yeah, you could get rid of that.
I think we get rid of that, but that 1.6 is if you assume that for time drifting or anything happen in a process, in a maximum phase delay, you get about 1.6 nanoseconds. Then you are getting about 4% core loss error. But right. In our measurements, we first do that calibration and get rid of that delay. But during the automation process, there's always a possibility that a drifting may happen. And we estimate that drifting to be 1.6 nanosecond.
Or
Thank
also
you,
like
Tom.
with a
Yeah, sorry.
with calibration, you can get, yes, better than 1.6 nanosecond, but you have also to consider that calibrating voltage and current in intrinsically difficult. Your calibration might also have parasitic effect. So it's not, you cannot also assume I am removing the skew between the current and voltage and I have absolutely zero. You will always, especially if you consider passive probes that can measure quite some voltage that are not 50 ohm matched, you will always, even if you calibrate, get some kind of delay that you cannot remove.
Thank you. That answers my question.
Any other question? Okay, so if not, we will conclude this webinar, and we will not, we don't have a planned webinar series in the near future. So thank you all for being with us in the past month, and we look forward to see the concept paper. So after concept paper, after we get a feeling of how every team's doing, we probably will reorganize some webinars to give an update of the competition and keep everyone on the same page. As we said, we want to make this competition not just about competition, but about all of us learning this interesting problem together and hopefully advance the knowledge. So yeah, with this, I will conclude this webinar. And if you have any question, private question, feel free to stay, and we'll be happy to answer any questions you may have. Thanks, everyone.